So the updated matrix now will be the following one. And already we have performed, we are done with forward elimination for the second column. So here we have 0, 0. And now this row is locked, okay? Because I am done with the second column. Now this row is locked. And then I should use a new pivot equation to continue my elimination, okay? So now I just still have one element to eliminate. But here I have a problem. If I take this row as my pivot equation, my solution will fail. Why? Because my pivot element will be equal to 0. And I can never accept this because a pivot element equal to 0 means that I am dividing a number by 0. So it's infinite, okay? And I cannot proceed. So now I am forced here to do pivoting, not just to reduce the round-off error, but because the solution will fail if I don't do pivoting. So here, the only choice I have, I just have one term below 0. The only choice I have is to pivot rows 3 and 4, okay? And then my pivot equation will be this one, and my pivot element will be 2. Okay, so now as we said, we cannot use this equation as pivot equation because the pivot element will be 0. So we must do pivoting. And now this is my final step to do. This will be my third pivoting equation. So this is the third pivot equation. And this will be my third pivot element. And it will be the final one. Okay. So now I still have one final step to finish forward the elimination. Okay. All I have to do now is to update these coefficients. Okay. To do this, I will define the factor. What will be the name of my factor now? Here, guys, do I need to do anything? Do I need to define factor? شو حيكون الفاكتور تبعي now؟ شو اسمه أول شيء؟ What is the name of the last factor I'm using? Since this element, okay, هو A43 أو إذا بدكم A second لأنه already we changed it A second for 3 فإذا الفاكتور تبعي حيكون اسمه F43 بس حيكون equal to 0 okay because this term is already 0 over 2 it's 0 so I don't need to do anything now this is an advantage لأنه already element can 0 وحطيته هون already it is equal to 0 no need to do any changes this equation will remain as it is and I am done I have transformed my matrix from a full matrix form to a upper triangular form exactly we don't need to continue Michelle. Okay so now all we have to do now is to do the backward substitution. So until now what we did is forward elimination. When forward elimination is complete, then we will end up with all elements below the diagonal are equal to 0. So we obtained this is called the upper triangular matrix because as you can see the elements are in the form of a triangle. All elements below the diagonal are equal to 0. Okay, so non-zero elements form an upper triangle. This is why we call it upper triangular matrix. And now you will see that the solution will become very simple to do. And we call it backward substitution because we will start by solving this equation. Why? Because for this equation, the coefficients of x1, x2, and x3 are 0. If I write the corresponding equation, it will be 5x4 minus equals to 33 over 14. So from this relation, I can get x4. So I deduce that x4 is equal to 33 over 14 times 5. Okay. Now I will repeat the same procedure to get x3. Now I will move to equation 3. Okay. From equation 3, I have 2x3 plus 2x4 equals to 5 over 7. So all I have to do now is to say that x3 is equal to 5 over 7 minus 2x4. So as you can see, equations are not coupled. You can, by proceeding in the backward way, you can solve for each equation will give you one unknown. So it's minus 2x3 over x4 over 2. And now I will continue to do backward substitution to solve for x2 and to solve for x1. So we can see this in this slide. Here maybe they didn't present it. Okay, let us continue. So for okay. So now if you want to find x2, okay, if you want to calculate x2, you will say that 7 over 3 x2 plus 7 over 3 x3, and x3 was already calculated from the previous step, minus 7 over 3 x4 also already calculated, so I know it, equals to minus 5 over 6. So now I can calculate x2. And if you want, we can develop the general rule is as follows. This coefficient, let's say, is called so if this is when you did the forward elimination, okay, this is called a prime 2 2, okay, this is called a prime 2 3, this is a prime 2 4, and this is b prime 2. So you can put in general, as a general solution, and x2 is equal to b prime 2 minus a prime 2 3 x3 minus a prime 2 4 x4 over a prime 2 2. Okay, so you can develop such general rules. All you have to do is to replace by the coefficients, and you can get your solution. And finally, you can develop a same general relation for x1. So x1 is equal to b1 minus a 2 1 times x2, okay, minus, sorry, it's a1 because this term, so when you do the name, this is a11, this is a12, this is a13, and this is a14, and this is b1. Okay, so it's b1 minus a12 times x2 minus a13 times x3 minus a14 times x4 over a11. Okay, So in this way, you can write a general rule for the backward substitution. Just you can replace coefficients by their values, and you will end up. Here, of course, it's easier for you to do it numerically, and أكيد no need to know general rule, because you can do it numerically in a fast way. So you just find x4 first, you move to x3, you move then to x2, then you move to x4. Any question on this? And it might seem for you that it's a long procedure. Yes, it's true, it's a long procedure. But if you compare with the number of operations you should do in Cramer's rule when you calculate determinants of very large matrices, you will end up with that the number of operation in Gauss elimination is much smaller compared to the number of operations in Cramer's method. Okay. Now, what is nice about your upper triangular matrix, okay, that you can easily get its determinant, okay, and you can always relate the determinant of the original full matrix to the determinant of the final matrix. And in general, if we don't do pivoting, we don't do any pivoting in the Gauss elimination process, the determinant of the original full matrix will be equal to the determinant of the upper triangular matrix obtained. Okay, but if we do pivoting, we can demonstrate that it will be equal or opposite in sign, depending on the number of pivoting operations we perform. So we can say that the determinant, you know, for an upper triangular matrix, determinant is the product of the elements on the diagonal. Okay, so the determinant of your final upper triangular matrix is A11 times A prime 22 times A second 33 times A third 44. Okay, and if you did pivoting operation, then you can say that the determinant of the original full matrix is equal to the determinant of the upper triangular matrix times minus 1 to the power p. So if the number of pivoting operation you performed is an even number, then you will get equal determinant. If the number of pivoting operations you did is an odd number, you will get same magnitude but opposite sign of determinant between the original full matrix and the final upper triangular matrix. Okay, so for example, if we check the example we did together, we did 2 times pivoting. Okay, and therefore p is equal to 2. So in the example we considered, the determinant of the original full matrix is equal to the determinant of the upper triangular matrix. Okay, and one of the advantages of upper triangular matrix is that the calculation of the determinant is very simple. تتذكروا قلنا 4x4 matrix, full matrix, is very hard to get the determinant. We need to do a lot of steps. But when we transform it to an upper triangular matrix, the determinant will just be the product of the elements on the diagonal, which is very simple to find. Now, as I told you, if we compare the number of operations required in Cramer and Gauss, we will see that we have a high difference, especially when we increase the number of equations to solve. Okay, you are not responsible of counting the operations. It's a little bit complex, and you need to know, you need to count. The idea you count every operation, addition, subtraction, multiplication. So if you sum all operations performed in Cramer method and in Gauss method, you can demonstrate, but as I told you, are not responsible of this to know how these formulas come from, okay, because it's a little bit complex. So Cramer rule, using Cramer rule, you need nearly the number of operation needed is of the order of n plus 1 factorial. While if you use the Gauss elimination method, the number of operations needed is of the order of 2n cubed over 3. And if you plot the number of operation required function of n, okay, then you will see that the Gauss method is much more efficient, especially for very high values of equations. And this is why I told you if you just have 2, 3 equations, it's fine to use Kramer. And the difference is not large between Gauss and Kramer. But as the number of equations increases, then Gauss will become much more efficient than Kramer method. Okay. The final part in this chapter will tackle 3 diagonal systems. Okay. In 3 diagonal systems, what we have is the form of the matrix is represent a certain particular behavior where you have zeros everywhere except in the diagonal, and just if you want uh, the line just above and just below the diagonal. This is why we call it 3 diagonal system. Okay. And such systems you can face a lot these configurations in engineering. Okay, so this is an interesting configuration to understand, and it will if you have such type of configuration, it will give you a much easier solution, and you can operate with it in a much easier way because you have a lot of zeros. Having a lot of zeros will reduce a lot your operations. You will reduce the number of additions, the number of subtraction, any operation that is required to find your final solution. And we can see this here. So for example here, because all of these elements are zeros, the first equation you write will be f1 times x1 plus g1 times x2 equals to r1. So instead of having plus a lot of elements, all of these, you don't look at them. In the computer, when the computer identifies that it's a 3 diagonal matrix, then it will allow him to reduce a lot the number of operations because he will not look at these zeros at all. Okay, and the equation will just be f1 x1 plus g1 x2 equals to r1. And if I continue, I can write other equations also in a simple way. So maximum I have in the second row to the row just before the last one, I will just have 3 terms in each equation. So if I take, for example, the corresponding equation here, it will be E3 times X2 plus F3 times X3 plus G3 times X4 equals to R3.